It's a bit strange imagining an audience. I suppose I can start now sharing the screen. Okay. I'm going to talk about some topics in gravity in comparison with electromagnetism. The reason is electromagnetic forces are very familiar to everybody. The only gravitational action we are familiar with is things falling under gravity, attraction of the earth, and so on. Whereas electromagnetism is present in every sphere of our life, from even down to the mobile phone signals and so on. Magnetism is familiar to every child, so it's a very familiar interaction. Now, just last Friday, there was a Nobel laureate discussion panel organized in UK about the greatest physics discoveries of the 20th century. Stephen Weinberg, William Phillips, John Mather, and Anthony Leggett participated. Now, none of them mentioned the perceived completion of the theory of gravity, that's a general theory of relativity, or electromagnetism, which is a special theory of relativity, as a highlight of the 20th century. Their preoccupation was the failed interpretations of quantum mechanics, unsolved foundational problems, and unknown aspect of cosmology. These are, of course, very important open problems. Surprising as this may be to this audience, the reason could be that most physicists do not study GTR, general theory of relativity and gravity, because the need is minimal. And there is almost nothing in the theory that challenges human ways of understanding, common sense, intuition, etc. The challenges are considered just mathematical. In contrast, every physicist needs quantum mechanics, but nobody claims to understand it in spite of one's other accomplishments. So quantum mechanics remains as a lifelong challenge. Is it really true that we understand gravity and electromagnetism completely? Okay, if you look at Einstein's general theory of relativity, it is now a century after its formulation. Most of it, or all of it, its predictions are now tested. Some examples are time dilation in a gravitational field, spectral shift in a gravitational field, deflection and time delay of light bending, modification of planetary orbits, which is called precession, magnetism like gravity, black holes, and the dynamical universe. And the last in the series, as you know, is gravitational waves. So we have seen all this, and we think we understand this theory, and it is a final theory of gravity. The focus of this talk will be to discuss some differences and similarities between gravity and electromagnetism, compare and understand electromagnetic radiation and gravitational radiation, understand the physical nature of gravitational waves, and then we will we'll have a brief look at the detectors of gravitational waves. There has been already many talks, so I will not go into the details there. Then we will think, how are the waves of interaction important for testing the theories? And finally, some two important questions. Is Maxwell electromagnetism a tested and confirmed theory? We think it is, but we should look at this question. Then, even more important, is Einstein's theory of general relativity the final tested theory of gravity? If you look at think about the first discoveries about gravity, Earth's gravity, it was mainly Galileo who studied this in some detail using inclined planes. Then there were several investigations by Huygens, Newton, who determined the values also. As you know, there is a story of Galileo studying gravity from the Leaning Tower of Pisa. He discovered the universality of free fall on Earth. So if you drop two objects, widely different object, widely different masses, they seem to fall. They fall at the same rate, same acceleration, which Galileo described in his monograph, which is translated as Dialogues Concerning Two New Sciences. Of course, even in India, we had opportunities to discuss this kind of universality of free fall. Many people must have seen this phenomenon happening, but our preoccupation was probably something different, with poetic vision and all that. Anyway, so universality of free fall is a very important aspect of gravity. Two things dropped in the gravitational field, they have exactly same acceleration independent of their masses or other material properties. This has been the basis for general relativity by Einstein. Let's see what it is. Anyway, testing this universality of free fall, there are many ways of testing. It has gone much beyond what Galileo could do or Newton could do. In fact, now we even test the universality of free fall using the Earth and the Moon falling towards the Sun as the two objects which is being dropped in the gravitational field of the Sun. This is called lunar. What is used as a technique is a lunar laser ranging, where you measure the orbit of the Moon precisely by sending laser pulses which are reflected back. So this is one way of testing universality of free fall. Another way of testing universality of free fall is using what is called a torsion balance or a torsion pendulum. When in the apparent motion of the Sun around the Earth, so you get a modulated signal for the free fall of two objects, which is used for construction of a torsion balance. So I will not go into details of that. I mention it here just to mention that I spent several years studying these aspects in our special laboratory, gravitational laboratory, in a place called Gauravithanur in Karnataka. It's an underground laboratory where we study this aspect experimentally. Now, it was Newton who discovered that gravity is a universal force. It can be extended, Earth's gravity can be extended to large distances, and the reason why an apple falls and the Moon going around the Earth, the same gravity which is controlling both. So here one can see that as the Moon goes around, it is also falling in the orbit. It is not reaching Earth only because it is going at a velocity in the orbit. But the free fall is exactly same as falling a stone from that distance. So he defined the law of gravity. He discovered the law of gravity, which is the inverse square law, Gm by r square. The force is, as you know, is Gm, the source, and the falling object divided by r square. This gravitational field can also be written as a gradient of a potential, where the potential is defined as Gm by r. So the gravitational field is the gradient of a much more basic, fundamental quantity called the potential. There is also a way of understanding Newton's law of gravity, the way Gauss understood it mathematically. It is in terms of the flux of field lines. If you imagine a gravitational field as a set of lines converging towards a source, then in a spherical area, which increases as r square, the density of field lines per unit, so number of field lines per unit area, density of field lines will obviously go as 1 by r square, because the area increases as r square, number of field lines per unit area will go as 1 by r square. So that's the understanding of a 1 by r square interaction in the Gauss's picture. Now, something important about this interaction. If you look at the laws of motion, if you look at the laws of interaction, gravity and electromagnetism, they are very similar. Gravity is gravitational constant, product of masses divided by r square. Electromagnetism, there is a proportionality constant, product of electric charges divided by r square, distance square. So these two laws are very, very similar in terms of the laws of interaction. Now, if you look at another law, which is fundamental in physics, it's Newton's law of motion. Given any force, whatever force, the acceleration is given by force divided by the mass. So F is any force, and mass here is called inertia. Now, surprise is the inertia in the general law of motion applicable to all instances of movement and forces seems to be the same as the charge of gravity. That is, what is appearing here as mass is actually the charge of gravity, just like electric charge is the charge of electromagnetism. Newton's law is completely separate from these two laws. Newton's law is different. The only common thing about law of gravity and law of motion is that one person, Newton, discovered both, but they are independent laws. But the surprise is that in both these laws, the same mass appears. Here we call it a mass, here we call it inertia, but it's the same quantity. It seems to be the same quantity experimentally. Now, the question is it really the same quantity? Is it a coincidence? Does it imply a deeper meaning? But once we accept that they are the same quantity, then the gravitational acceleration, the acceleration of a body under the force gravity, the m cancels out. So it is independent of the mass. To see the importance of this, look at the electromagnetic law. F is equal to product of charges divided by r square. But the law of acceleration is still the same law with a mass in the denominator. So when you look at electromagnetic acceleration, you see the mass doesn't drop out. It's not independent of mass. It is not independent of charge. It depends on the ratio of the charge to mass. So gravity seems to be a very special interaction. Inertia seems to be identical to the gravitational mass. And it's called the weak equivalence principle, the equivalence between inertia and gravitational mass. Now, when Newton looked at the way forces appear, he had this following dilemma. If you observe an object moving uniformly, kinematically it's the same situation if the frame of reference is moving the other way. You cannot distinguish these two if the motion is extremely uniform. So inability to feel or detect genuine uniform motion is called a principle of relativity. Is one aspect of dynamics. Even Galileo studied it. However, look at the following situation. There is a reference frame which is rotating, and there's a mass inside that. Nothing happens to the mass. I'm in a room it is rotating, but something is floating in air, nothing happens to it. However, if the object is rotating, a centrifugal force appears. A real force appears which tend to take the object outside from the frame. So such forces are called pseudo forces or fictitious forces. They have no origin, in the sense they have no source. They are proportional to mass, but their origin is not understood. But that way, Newton could incorporate them into his laws of motion. There you can write the total acceleration as applied force divided by m plus the inertial force divided by m. But the inertial force is always proportional to mass. Therefore, that is independent of mass. Just like gravity. So sensible forces appear with uniform, non-uniform motion. The force is proportional to inertia. So gravitational force is also proportional to mass. The question is, why is also inertial force proportional to the same quantity? We have two instances where the force is proportional to mass and the acceleration in motion. Acceleration is independent of mass or material properties. One is gravity, one is inertial fictitious forces. Okay. How did the three pioneers looked at this problem? Isaac Newton linked the inertial forces to the reality of absolute space. That is described in his Principia Mathematica. It was in 1670. Ernst Mach, the physicist philosopher, speculated that the origin of inertial forces was some interaction with the matter around in the universe. Of course, he didn't say gravity at that time because that was not enough with the known amount of matter in the universe. But yet, he made a speculation that the origin of inertial forces could be in some interaction. That is 200 years after Newton. 25 years later, 30 years later, Albert Einstein asserted that gravity is also a fictitious force. Gravity is not a real force. It's a fictitious force like acceleration, because gravity appears in an accelerated frame and it disappears in a freely falling frame. So let's look at it in some more detail. We know that two objects which is dropped fall under gravity in the same acceleration. If there are two objects floating in a room without gravity, with no gravitational field present, and if the room is accelerating upwards, you see exactly same as what you saw in the case of gravitational field. So let's look at again. Two objects falling in a gravitational field and the room accelerating upwards with this value A is equal to minus G. You see exactly same kinematics. So gravitational field G and the acceleration or accelerated frame seems equivalent. This is called the Einstein equivalence principle. It's a step higher than the weak equivalence principle, which asserts the equivalence of inertia and mass. This is the equivalence of gravitational field and acceleration, local equivalence. This is called the Einstein equivalence principle. It's also same as saying that in free fall, in a satellite, for example, there is no gravitational field. The correct statement is a gravitational field cannot be sensed in free fall. But it does not mean that in free fall there is no gravity. That's the next step we should go to. If you consider the free fall in a gravitational field, they have the same acceleration, but you see the separation between these two objects changes as they fall towards the center of the Earth. So there's a slight curvature here. These objects started with some separation. At the end, they have a slightly different separation. But on the other hand, if you have an accelerated room, the separation doesn't change. They fall at the same rate, but the separation doesn't change. Similarly, if you drop two objects here with a slight separation, not at exactly same level, just a slight separation. Since the gravitational field increases as you go towards the Earth, as they fall, the separation increases. But in an accelerated room, nothing happens to the separation. It remains the same. So there is a difference between accelerated frames and real gravitational fields. And they are called tidal forces, tidal deviations. Two things coming together, or two objects going farther when they are falling vertically, that is called a tidal separation. This is exactly why tides happen on Earth. They cannot be eliminated by freely falling. So tides seems to be the genuine signature of gravity, and that is how it is. That is a basic idea of general theory of relativity. Tides are quadrupolar in the sense here we saw in this direction these two objects came closer, whereas here these two objects became farther. So depending on the direction in which you are looking at the tidal forces, they have different character. Here it is attractive, there it is repulsive. So they are called quadrupolar. We will come to some details later. So let's compare gravity and electromagnetism. Is the only similarity between these two forces is the inverse square law. If you look at electricity and magnetism, there's an electric field. And now if you have moving charge, there's also a magnetic field. But magnetic field is only there only when the motion is present. When the charge stops, magnetic field disappears. So magnetic field is transient. Essentially what we call a magnetic field. Magnetic field is our own imagination. It's a free creation of human mind, started with Faraday. But what we really call a magnetic field is the current of electric charge. So once we have the magnetic field and the electric field, charges and currents, as you know, described in Maxwell electrodynamics. Once we have this, we can have waves of electromagnetism which propagates and so on. That's the theory of electromagnetism. So in gravity and electromagnetism, when you make a comparison, both have electric and magnetic parts, charges and their currents. In gravity, mass is a charge of gravity, and momentum, mass multiplied by the velocity, is a current of the charge of gravity, momentum. It's the equivalent of current in electric current in electricity, electromagnetism. One important difference between the two is that while electric and magnetic fields have no electric charge, gravitational field has a gravitational charge. This is very peculiar. What I mean by this is that because of the equivalence of the mass and the energy, all forms of energy is equivalent to mass. But masses always generate gravity, and hence gravitational field itself, which has energy, will generate its own gravitational field. Therefore, all fields, including the gravitational field which carry energy, also generate gravitational fields. This is one reason why the theory of gravity is complicated to work with. It's a non-linear interaction because gravity generates its own gravity, that gravity generates its own gravity, and so on it goes. Now, if you look at gravity and electromagnetism, we know that we have these two charges and currents. The question is, what about relativistic gravity? We know that static gravitational charge generates a gravitational field. Does moving and rotating masses generate a field which is very similar to magnetic fields in electricity, electromagnetism? Let's look at it. We are familiar with magnets. Now, a magnet is very similar to a coil in which there is current. Both are equivalent. Anyway, all magnets are just charges or moving charges. Now, if you consider two currents which are parallel, we know in electromagnetism they attract. Parallel currents attract, the opposite currents repel. What about gravity? It turns out that in gravity also there are similar effects. which are very small. Therefore, we don't see it in everyday experience. If you have two masses which are moving together, they repel. Similarly, if there are two objects which are rotating nearby, they attract. They attract because if you look at this thing here, while this is rotating in this direction, that is rotating in the opposite direction. So nearby, these are opposite currents. These are equivalent to opposite currents nearby here. Therefore, they attract. So in gravity, parallel currents, masses which are moving in the same direction repel, and masses which are moving in opposite directions attract. This kind of a thing, general theory of relativity predicts. The experiments show good evidence for that. So there is what is called gravitomagnetism, similar to magnetism of moving electric charges. In fact, if you have a large shell of mass, a very large room with some mass at the on the walls, and if such a object rotates, and if you are at the center of this rotating large room, you also feel a certain rotation. It is given by a formula like this. What you feel is a very small fraction of the rotation of this bigger room. A small fraction is given by this quantity gm by c square r, which is much smaller than 1 for objects like Earth. Whereas if you go to near a black hole, this becomes very, very large. Anyway, the real gravitational field near Earth, therefore, is a familiar gravitational field because of which we are staying on the surface of the Earth, plus a very small field which is extremely difficult to detect, but it is also a gravitational field. I'm not showing magnetic field of the Earth. That's of course there. This is a gravitomagnetic field of the Earth. The only way to detect this is to put a gyroscope in orbit around the Earth, because in a magnetic field, if you have a magnetic moment, it will precess. So similarly, if you have a gyroscope in the gravitomagnetic field of the Earth, it will precess, and people have measured this. In fact, if you go and look at what's called Gravity Probe B of Stanford University, there's a description of such experiments where the gravitomagnetic field of the rotation of the Earth is detected. We don't go into details there. So the structure of electromagnetism and gravity is similar. It has potential field and tidal field. Both are very, very similar. Now, mathematically, in electromagnetism, we have the potential, which is Q by R, charge by distance. And then there's an electric field, which is the gradient of the potential, which is the inverse square law. Then there's a divergence of that electric field, which is a Poisson's equation, which is proportional to charge density. And the law of motion is, of course, Newton's law of motion, where the force is electric force as well as magnetic force. Now, for moving charges, there is a vector potential, which is just velocity multiplied by the electric potential. And the curl of that is a magnetic field, as you all know. And also, if this vector potential is time dependent, there is an electric field. Similarly, in gravity, when you look at the linear case, instead of considering all the nonlinear aspects, there's a potential, gravitational potential, which is gm by r. There's a gravitational field, which is the gradient of that potential, which is gm by r square. Then there's a tidal field, which is a divergence of this gravitational field, which is given by, again, a Poisson's equation. Moving masses generate a gravitomagnetic potential, which is exactly similar to this, V by C multiplied by the gravitational potential. The gravitomagnetic field is a curl of gravitomagnetic potential. And similar to electromagnetism, if the gravitomagnetic field is time dependent, there's a gravitational field. And the force, the law of motion, is very similar to Newton's law. However, because of the equivalence principle, you cannot measure this acceleration if you are also in the same position, because you will also accelerate with the same acceleration. Therefore, only the differential acceleration between two different objects which are far away, have some distance, just like what we saw, objects falling together. If they are very close, we will not detect, but there is some separation. As it falls, the separation changes. It decreases or increases depending on the direction which is measurable. So only thing which is measurable in gravity is tidal accelerations. So what can be learned from the small number of facts which we discussed so far? Gravity is very much like electromagnetism. It's a long-range interaction, but gravity is non-linear. The energy in gravitational field is also a source of gravity. Because of the universal equivalence of mass and inertia, geometrical description of gravitation interaction is possible. Because of the falling object is not important. It drops out of consideration because everything falls with the same acceleration. So you can forget about the bodies which are falling and talk about only the gravitational field and its properties. So the dictionary from interaction to geometric description is the gravitational potential is called a metric of this geometry. I will explain it slightly better. The gravitational field is called the derivative of this metric, the gradient of this metric. Sometimes it's called a connection. Then the tidal fields, tidal accelerations are called curvature. There are very important physical effects even when the curvature is extremely small. In fact, the curvature near a supermassive black hole, 10 to the 8 solar masses, is even smaller than the curvature near the Earth. What I say is, the Earth's tide, we can just look at the ocean and see these tides every day, very large tidal effects. These are the effects of the gravitational curvature of the Earth. Such tidal fields near a supermassive black hole is smaller than the curvature near the Earth because it depends on mass by r cube, the distance cubed, instead of, whereas properties of the black hole depends on mass divided by the radius of the black hole. That is something which we will not go into this talk, but just I want to mention that just because the curvature is, just because there is a strange objects like a black hole, it doesn't mean that the gravity, the signature of gravity, the curvature is very, very large near every black hole. But near a neutron star or a solar mass black hole, this curvature is extremely large, much bigger than the curvature near the Earth. Now we try to understand gravitational waves, which is the topic of this lecture series, with the understanding of our understanding of electromagnetic waves. Now, if you look at the electric charge, you know that the electric field is radial. And let's say the charge starts moving, it accelerates, starts moving like this. So it moves by a short distance. What is the electric field of this charge which has already moved some distance? Near the charge, the electric charge should be radial with respect to the new position of the charge. But far away from the charge, it should be the old electric field because the change, the fact that the charge has moved from here to there, has not, that information has not reached far away. That information has reached only a distance c times the time. Okay. So nearby, the electric field is radial with respect to the new position of the charge, up to a distance of ct. But beyond that distance, it's an old field which is centered on this charge. So therefore, the charge, the electric field looks like a kinked electric field. It has a radial part and then there is a transverse part. Then it joins the old field. So this is the shape of the electric field of a accelerated charge. Therefore, this is what we call radiated field. This kink moves at the speed of light as time progresses. That's what we want to study. So there is a radial field E square, ER, which we know is Q by R square, and there's a transverse field which we want to calculate. How do we calculate that? Because we know this ratio. The ratio of this to this we know, because this is same as this motion of the charge, Vt. And as the angle changes, of course, this vector displacement of the charge, its component which we want to take, so it's sine theta. So Et is Vt sine theta. Er, of course, is C times T. Okay, so we have this ratio. And looking at this, we know that the acceleration, the V itself is acceleration multiplied by time. So this is, and one time cancels out. Therefore, it is acceleration multiplied by time divided by C and sine theta. And since this distance is the distance up to which the radiation has reached, R, we have this formula. So the ratio of transverse field to radial field is just AR sine theta by C square. But we know what ER is. It is Q by R square. Therefore, we can write immediately the value of this transverse field. It is this. Now, Q times R is called the dipole moment. Therefore, we can say that this is the second time derivative of this distance, and we know that it is dipole. It's the same as Q is a constant. Therefore, you get this formula for the transverse field, the radiation. So this is a radiation formula which we got from very simple consideration of geometry. And this is called a dipole radiation formula. In fact, this is exactly the formula which you derive from Maxwell's equation. There is no difference. It's exactly the same formula. It's called a dipole radiation formula. In fact, we said in the Gaussian Gauss picture, the radial field goes as 1 by R square because the area of the sphere increases as R square. Here, it's a transverse field. It is like a circumference which increases as only radius R. Therefore, the transverse field goes as 1 by R. And since this is 1 by R and not 1 by R square, it can be felt very, very far away. Now we can ask, can we expect gravitational waves if the basic physics is similar? If that is the case, the transverse field of the gravitational radiation also should be given by the same formula, where the electric charge is replaced by gravitational constant multiplied by the mass. Rest should be exactly the same. I should write R here. R squared. It's exactly the same. This is R. It turns out it is not true. So let's look at what an electromagnetic wave is. If a charged particle is attached to some base with a spring, and if it oscillates, we know that periodic electromagnetic waves are generated. That's what we get when we generate a high frequency wave for various applications like radio, mobile phone, and so on. So accelerated electric charges is what generates electromagnetic waves. What about the accelerated mass? Can we expect gravitational waves from an oscillating accelerated mass? It turns out no. That's because this picture is wrong. The mass oscillating like this is wrong, attached to another mass, because the momentum has to be, total momentum is a conserved quantity. If this goes back and forth like this, the other mass also has to oscillate. Let's say this is a very large mass. However large it is, if one mass oscillates, the other also has to oscillate. This doesn't apply to the case of electric charge, because one can be charged, whereas other can be neutral, not charged. Whereas there is no object without any mass. If a mass is attached to another mass, both have to oscillate in opposite senses. the momentum, total momentum conservation. Therefore, both will emit radiation, exactly like any accelerated mass, but they cancel out. Therefore, gravitational waves cannot be generated with two masses like accelerated masses. Similarly, in this direction, there is no radiation anyway, even in electromagnetism. So this shows that total momentum conservation says that there cannot be any gravitational radiation. Except that if you look at a direction which is not this or this direction, just look at an intermediate direction, then there is a difference when these masses are oscillating because they have a phase difference. This one, which is being closer to observer here, emits the radiation slightly earlier, and this one slightly later. There's a phase difference, which is given by this omega r cos theta. This is a standard formula which we got from electromagnetism, and we saw that is zero. Then there's a phase difference. This is a product. So it's a product of these two quantities, which is what we call as gravitational waves. The transfer field of oscillating masses is a gravitational radiation is given by this formula. And you can see it has a different property than electromagnetism. That is, at every 45 degrees, it becomes a maximum, and then it becomes zero. It has a quadrupole. It's called a quadrupole. Every 45 degree. From horizontal direction, if you go to 45 degree, it has maximum. Then it goes to zero. Then again maximum. Then zero, and so on. And therefore, its polarization is given by a 45-degree rotation. There are two polarizations. One polarization is different from the other polarization when you rotate through just 45. This is called a quadrupole pattern. Now, we know that, so let's say this wave is coming and we want to detect it. However, if we have an object here and we are standing nearby, both of us, the test object and the observer, both will accelerate in this gravitational radiation field equally because of the equivalence principle. So we will not be able to see the gravitational waves with a local detector. We need a very special detector to detect gravitational waves. This is because if you are in the same frame, everything accelerates the same way, we cannot feel gravity at all. We will think that gravitational waves is never there. So only tidal effects can be measured. In the sense, we have to find a detector which is measuring the gravitational acceleration at two different points. So not this, we cannot detect this, but a gradient of that in the transverse direction. So I have put the formula here. This one is approximately this formula divided by the wavelength, or a fraction of the wavelength, which is the difference in the field separated by some distance. Lambda by 4, because that is when you get the maximum difference. That's the differential acceleration, which is proportional to the gradient multiplied by the separation. Now, the displacement, once you know the acceleration, the displacement is half at square, but t square is 1 by omega square. Okay, therefore, if you look at this formula carefully, you get a final formula like this. That is, if you have two objects, the tidal separation maximum will become delta L, which is of course proportional to L because it's a tidal field, multiplied by this quantity. Therefore, delta L by L, what we call strain, is given by this formula. R omega is velocity, and we get what is called the quadrupole radiation formula, derived by Einstein from general relativity. Here we have derived, maybe we have used slight approximations, but it's almost exactly the same formula, just from analogy with electromagnetism and so on. But this derivation teaches us something very, very important. Actually, this strain is not the change in the potential. It is not a change in the metric. It's actually a tidal field in the transverse gravitational field of which is radiated by oscillating masses, accelerated masses. It is in fact a tidal field. So, though it is usually called a metric perturbation, it's actually a tidal field, it's a propagating tidal field, and this is a formula for that, which is very familiar from various talks in the series. What is the action of a gravitational waves on masses on Earth? If you look at the action of electromagnetic waves on charges in a metal wire, like an antenna, every metal wire has a charged particle, free charge particle. When the waves hit this charged particle, they oscillate back and forth, which generates a potential, electric potential voltage across this charged wire, across this wire, and that's what we detect as a electromagnetic wave. When a gravitational waves arrive from masses which are going around, which are oscillating there are no oscillating masses, there are only masses which go around each other like binary neutron stars, which is like oscillations in two directions. The waves come. If you have only one mass, it will of course accelerate, but an observer who is nearby this also will accelerate similarly, so you cannot detect the oscillations of one mass. You need two masses separated by a distance. And if you use this formula, which we had so let me go back. So this is a scheme. The gravitational waves arrive and we have two masses separated by a distance, and the differential oscillation between these two masses is what we want to detect. You will see that it's a very small change in the length which we have to detect. And as I said, gravitational waves are quadrupolar. In one direction it is attractive, and then the other direction is repulsive kind of action. So this is what will happen if you have four different masses, exactly like the tidal forces. But here the tidal forces are oscillating. That's why we see this. And as you notice, and as you have heard in many, many talks, the tidal forces, the Michelson interferometer is a natural detector for this, because it detects the differences in the movement of masses. When one mirror is moving towards this beam splitter, the other mass is moving away from it, like this. There's a difference, and that differential motion is what we detect. So it's a natural detector for gravitational waves. You have heard many, many talks on the detectors of gravitational waves. And from this formula, we can calculate the strain because we know the masses of objects. We know the gravitational constant. We know the typical maximum velocities. Even if you assume 10% of the velocity of light for the oscillating masses, the strain is very, very small, as you know, 10 to the minus 19 meters for two masses which are separated by 1 meter. And that's why we need gravitational wave detectors which are kilometers in size, so that this strain is this side. Therefore, the separation, the displacement can be increased. Now, the Michelson interferometer, as you know, is very, very sensitive because it uses light, whose wavelength is in micron scale, and we can measure the phase difference between light waves very, very accurately using precision metrology. And that's how we detect these small changes. The point is that every bit of innovation counts in this game, because, as you know, the wave strength reduces only as 1 by r. The strain reduces as only 1 by r. But if you take a volume of radius r, the total number of astrophysical sources inside this is proportional to the cube of the radius, the volume. So therefore, if you increase the sensitivity of the detector by a small fraction, it can access the number of sources which goes as a cube of the improvement in the sensitivity. Okay, that's why it is very important. Even small innovations which might increase the sensitivity of a detector by 20% or 30% can lead to the detection of double the number of sources. And as you know, a gravitational wave detector is a sophisticated Michelson interferometer. I don't want to go into any of the details because there have been many talks on the principles and technology of this kind of detectors. So the LIGO Virgo detectors all of them have the same kind of configuration, where this distance is given by 4 kilometers or 3 kilometers. They are very gigantic Michelson interferometers. Now, Einstein's theory doesn't speak in the language of potential sun fields. It talks in the language of metric, connection, curvature, and so on. The reason is equivalence principle. If all bodies have the same dynamics independent of mass and other properties, then the body drops out of description. That's not important. Further, gravity affects both time of the clocks and distance between particles. Therefore, gravitational potentials can be replaced by the modification of time and distance by the potential. That is, factually there is a gravitational potential, gravitational field, tidal field, and so on. But since gravitational potentials can affect time and distance, you can replace gravitational potential by the modifications of time and distance. Let me explain this. What is called a metric? If you have a vector, some distance, if you have a distance from this point to that point, it can be resolved in two directions like dx and dy. And the distance square is given by the Pythagoras law, dx square plus dy square. Square of the distances add, you get the length of this vector. Now, the coefficients here is essentially what is called the metric. So gxs, the coefficient here is 1. Here also it is 1. So the metric is. On the other hand, if you use spherical polar coordinates in the plane here, r and theta, the distance, the distance square is not given by this formula, but a different formula, dr square plus r square d theta square. Here now, the coefficient here is 1. There it is r square. The metric has changed. So the metric in polar coordinates is completely different. But the distance is the same. That has not changed. Similarly, in relativity, we talk about a four-dimensional space and time, dx square minus c square dt square. You can see by the same analogy, the metric is 1 for space and minus 1 multiplied by c square, which is a scale factor. So now the question is, entire theory of general relativity talks in terms of the modifications of the time intervals, durations, and spatial intervals, distance between masses. Therefore, it talks in the language of metric changing because of gravity. You know that if you have two clocks, which is separated by a distance in the gravitational field of the Earth, the potential here and the potential there are different. Therefore, there is a gravitational time dilation between these two clocks. These two clocks run at different rates, and I will talk about this more in the next talks on Friday. It is related to the potential. Similarly, if you have a length scale, like a wavelength here, which is propagating upwards, radiation propagating upwards, the wavelength changes. This is called gravitational redshift, which is one of the first predictions of general relativity, even before the full theory was completed. Again, it depends on the potential. The potential here is different from the potential there. Therefore, you can equate the potential to the changes in the spatial distances or the metric. So the metric is modified by the local gravitational potential. Therefore, potentials can be represented by the metric itself. Then the gravitational field can be represented by the first derivative of the metric, because gravitational field is the first derivative of the potential. And the tidal forces by the second derivative of the metric, because tidal forces is the second derivative of the potential. So gravitational curvature is essentially this tidal forces. Second derivative of metric is called the gravitational curvature with appropriate terms. So therefore, that's a connection between physical gravity and geometric gravity. This relation is Einstein's equation of general relativity. It's a generalization of the Poisson equation, taking into account of various currents, gravitomagnetism, nonlinearity of gravitation, everything put together. Therefore, it's a geometry in general theory is an encompassing description, and there is no logical path to conclude that physical gravity is geometry, though many people say that. Physical gravity is gravity, and there's a convenient geometric description, which is, of course, a very encompassing in the sense it includes everything. There is no experimental comparison either. All statements on space-time are unprovable, because space-time is not observable. It's an unobservable entity. It's not a physical entity and cannot be demonstrated. What one can demonstrate is only effects of matter on matter in terms of clocks changing their rates and length between material particles changing. In fact, I wanted to quote two quotations. One is by Steven Weinberg, who wrote this very famous book on gravitation and cosmology, which we all use. However, I believe that the geometrical approach has driven a wedge between general relativity and the theory of elementary particles. As long as it could be hoped, as Einstein did hope, that matter would eventually be understood in geometrical terms, it made sense to give Riemannian geometry a primary role. But now the passage of time has taught us not to expect that strong, weak, and electromagnetic interactions can be understood in geometrical terms. And too great an emphasis on geometry can only obscure the deep connection between gravitation and the rest of physics. And I also wanted to quote another saying by the creator of the theory himself, Einstein, the letter to Lyndon Barnett, 1948. He says, "I do not agree with the idea that general theory of relativity is geometrizing physics or the gravitational field. The concept of physics has always been geometrical concept, and I cannot see why the metrical field should be called more geometrical than, for instance, the electromagnetic field or the distance between two bodies in Newtonian mechanics. The notion comes probably from the fact that the mathematical origin of metrical field is a Gauss-Riemann theory of the metrical continuum, which we won't look at as part of geometry. I am convinced, however, that the distinction between geometrical and other kinds of field is not logically formed." So gravitational waves and space-time. Many people say gravitational waves are ripples in space-time continuum. You can say that it's a way of saying it. However, Feynman wrote a book. He studied gravitation, and he wrote a book on lectures on gravitation, in which he describes how to study gravitation, exactly like how we study electromagnetism or other forces of standard model, using his Feynman diagrams and treating gravity as an interaction. And of course, there when you do quantum theory, there's gravitones and so on. I'm not going into what he did at study. There are a lot of complications, of course, infinities and so on. But I want to state that if the gravitational waves are ripples in geometry of space-time, and if somebody claims that that's the only way to see them, then they cannot become particles on quantization. If you talk about geometry of space-time, it is geometry. You cannot get a particle on quantization. Quantizing space-time geometry can at best give you quantized geometry, a la Ashtaker's formalism, for instance. They are not Feynman's graviton. So one has to be very, very careful when you mix up this concept of ripples in space-time and gravitons and so on. You cannot talk them in the same breath. They are completely different objects. Now, I want to complete this talk by asking this question. Is Maxwell electromagnetism a tested and confirmed theory? Is Einstein's gravity, Einstein's general theory of relativity, a completely tested and confirmed theory? Let's look at electrodynamics. I will give only one example. This is the first paragraph of Einstein's special relativity paper, 1905. He says, it is known that Maxwell electrodynamics, as usually understood at the present time, lead to asymmetries which do not appear in the inherent phenomena. Take, for example, the reciprocal electrodynamic action of a magnet and the conductor. Depends only on the relative motion of the conductor and the magnet. What he's talking about is, if you have a magnet north-south, then there is a conductor on top of it. And so you can move the conductor and the current will flow. Every schoolboy knows this. But you can also move the magnet. The same current will flow. Both give you the same, exactly same result. And then Einstein says, therefore, there is no point talking about absolute motion, absolute rest, and so on. Everything depends on only relative velocity. What he says is, you can move the conductor. There's a current which is flowing. You can move the magnet. Same current will flow. The formula is given by V cross B for the potential which is generated. Now, therefore, if you move both together, nothing will happen because the north down south, and you can rotate it. You can either rotate the conductor, so the conductor is moving relative to the magnet, or you can move the magnet is moving relative to the conductor, or you can move the whole thing together. There is no relative motion. Now, Faraday studied this extensively. And there are other people like Ampere also studying. And it is described in his nice lecture, thrilling lecture called the Beckerian lecture, Experimental Research in Electricity, Faraday. So he did this and he found that the current flows. There is, of course, relative motion, there is a current flows. And the formula is given by the same V cross B and all that. Now you can move the magnet. And then he was very, very surprised because there is no current. There is relative motion, but there is no current at all. You can move the whole thing together. There is no relative motion. Now there is a current. This is a very easy experiment to do. Many people do this experiment. Everything rotating together without any relative motion. There's a very large current, exactly same as the current here. So this is one example where what is written in this paper is not correct. It is not dependent on only the relative motion of the conductor and the magnet. It depends on something much more profound. We will not talk about what it is. Another is on the propagation of light, for example. This general relativity as well as special relativity requires the propagation of light with an invariant relative velocity. You read this writing by Charles Nordman, who was a friend and admirer of Einstein, a radio astronomer. However, there is still something infinitely troubling in the Einsteinian system. This system is unbearably coherent, but it rests on a particular conception of propagation of light. How are we to imagine that propagation of a ray of light could be identical for an observer who flies away from it and for an observer who rushes towards to meet it? If this is possible, it is in any case inconceivable to our customary mentality. And no matter how hard we try, we cannot make the mechanism and nature of that propagation intelligible. That's all. And he says, it must be confessed that here lies a mystery which eludes us. The whole Einsteinian synthesis, as coherent as it is, rests on a mystery, exactly like the revealed religions. I'm sure each one of you have wondered about this question. How can light, relative velocity of light, be an invariant? nobody is able to explain, but most people just believe it. But it has never been verified in any experiment. Many people think that these are routinely verified in experiments. And I want to show you one thing which might be a revelation for you. This is Astrophysical Journal, 1925. It's a paper by Michelson, who did the Michelson-Morley experiment. Of course, he should know whether his experiment was a proof of the invariant velocity of light. He writes, effect of the Earth's rotation on the velocity of light. In 1925, writes, theory of the effect of rotation of the Earth on the velocity of light as derived on the hypothesis of a fixed ether. And then the next paper in the same journal, it's an experiment which he did with Henry Gale, in which he says the beam traversing the rectangle of a counterclockwise direction was retarded. The velocity was actually reduced. The observed displacement of the fringes was found to be some quantity, 0.23, agreeing with a computed value, 0.236, with the experimental error. Confirming this theory, which is calculated on the hypothesis of a fixed ether. I'm not saying all this just to say that there is ether and so on. What I'm saying is, stressing here is that don't believe what the textbook says when they say the relative velocity, invariance of the relative velocity of light is confirmed by this and that experiment. It is not correct, as you can very plainly see from these examples. So, is Einstein's general theory final test such theory of gravity? We know that already there are unexplained things in Einstein's theory. Of course, cosmology is already complicated, and people think that maybe the theory may have some modification, but that's a vast subject, cosmology. If you look at centrifugal force, if a frame rotates, nothing happens to an object which is just staying in the room, but the object itself rotates, there is an outward force which we call centrifugal force. Or Coriolis force, which seems important in explaining tropical cyclones. And nobody knows, even after a complete theory of gravity is there available to us in general theory of relativity, we don't know the origin of this simple everyday forces like centrifugal force and Coriolis forces, the forces which causes things to bend in a rotating system. The origin of inertia, origin of inertial forces, these are unknown even today. So Isaac Newton, as I said, linked inertial forces to the reality of absolute space. Mach speculated that the origin of inertial forces was some interaction with the matter around in the universe. Albert Einstein asserted that gravity is also a fictitious force. Gravity is not a real force. It's a fictitious force which can be made to disappear by going into a freely falling frame. However, the fact is that the inertial forces are indeed gravitational. I have not proved it, but I can prove it. Their origin is a gravitational interaction of a body with all the matter in the universe. Much like Mach said, it can now be proved experimentally. This will turn out to be the incompleteness of Einstein's general theory of relativity, exactly as the present-day electrodynamics also look incomplete. The example which I showed, the Faraday's experiment, which Einstein was not aware of. So the correct statement is that inertia is indeed gravitational, and not. It is not correct to say gravity is inertial. What GTR asserts is gravity is inertial. It is fictitious. No, inertia is gravitational is the correct statement. And the difference is very, very important. It is as important and far-reaching as the difference between Ptolemy's geocentric system and Copernicus' heliocentric system. So we will see a glimpse of this difference for measuring and managing time in my next lecture on 7th hours. And I stop here. Thank you very much. I seem to have finished almost on time. That's a miracle. I'm a bit slow. Hello. I'm trying to see both together. But, okay, I just read out. First question is there any work towards measuring gravity gradients in the torsion pendulum at Gravitational? See, we actually want to avoid gravity gradients because gravity gradients always make things move. That is not what we want to study. We want to study the equivalence principle. So therefore, the gravity gradients, the forces on the two sides of a torsion balance has to be absolutely equal, not different. Tidal field, the gravity gradient generates unequal forces. So there is no interest in studying gravity gradient because a simple tide is a gravity gradient. So you have to avoid those gradients to study these things. Next is, can you explain gravity in a simpler form? I thought I was describing gravity in a very, very simple form in analogy with electromagnetism. But gravity is simple once you understand electromagnetism. The complexity is in its non-linearity because energy being equivalent to mass, gravitational field generates its own gravitational field, and it's a non-linear process. So that is the difficulty. That's why people like Balayer has to spend years and decades calculating higher and higher order corrections to gravitational waves. Somebody has asked, is gravitation a scalar field? I don't think you should have asked that question because first of all, we saw there's a gravitational field exactly like an electric field, which is not a scalar field. We also saw there is magnetism like gravity, a gravitomagnetic field. So gravitation is a complex field in that sense. Three components of electric-like field, three components of magnetic-like field, and so on. So it is certainly not a scalar field. Okay. How and why do masses moving in the same direction repel? Okay. It's a relevant question. We know in electromagnetism, charges moving in the same direction, parallel currents, they attract. If you pass current through two wires which are nearby. If you pass parallel currents, they come together. And if the currents are opposite, they repel. So parallelly moving charges attract, and parallelly moving electric charges, charges which are moving anti-parallel, repel. Now, in electromagnetism, you notice that equal charges repel, right? A positive charge repel a positive charge. But in gravity, a positive mass attracts a positive mass. So in gravity, everything is reversed compared to electromagnetism in terms of these forces. So it's a simple way of saying that such a difference is reasonable. That in gravity, parallel currents, that is, if two masses are moving parallel, they attract, they repel, is reasonable, because in electromagnetism it's exactly the opposite. I have not shown the whole derivation, but you can see from the comparison, that's the way one would expect. If gravity isn't a force, just a consequence of curvature of space-time according to GR, why are we interested in unifying gravity with other forces? We cannot unify gravity with other forces if we maintain that attitude that gravity is not a force. This is exactly what Weinberg was saying. In fact, what the quote I showed you, Stephen Weinberg, is exactly what he's saying. If there was a difference in the way we treat gravity and the other forces, there's a wedge driven between the theory of gravity interaction and the other interactions. You have to change that. So, okay. Half of the talk was really showing you why it happens. So let me go back to the screen. Let me see whether I can show it again. You look at this. Look at the simple situation in which two objects are just falling. They fall towards Earth, but they also come closer here. Similarly, when two objects fall one after the other, their separation increases. So in two directions, in one direction they came to closer, in the other direction they went farther. The separation increased. So this I called already a quadrupolar pattern, right? Here I showed that this is in one direction it is coming closer, the other direction it is diverging. This is I called as a quadrupolar pattern. Now, if you look at the radiation, which we talked about, the real reason, the physical reason. In the case of an electromagnetic wave, when the charge oscillates, you get the dipole radiation. So the charge oscillating back and forth, and you get a dipole pattern of radiation. But when you rotate 180 degrees, it has the same pattern. However, for a gravitational radiation, when one mass is associated with other mass, like two masses going around or two masses at the end of a spring, the total momentum has to be conserved. Therefore, if one mass is oscillating up and down, if one mass is oscillating up, the other mass has to oscillate down. They have to be completely out of phase, exactly out of phase in their oscillation. Therefore, the dipole radiation cancels out. It cannot have a dipole radiation. Whatever electromagnetism, this was a charged object, the other was an uncharged object. Therefore, you could have a dipole radiation. But here, You have dipole radiation, but completely out of phase, which is as good as no radiation. That is why you have the next level, the quadrupole radiation, because dipole radiation cancels out here. Here there is no dipole radiation in the perpendicular direction, but the difference of two dipole radiations, the difference because of a phase difference, is what we call quadrupole radiation. There's only one radiation, one transverse field, whether it is dipole or quadrupolar or multipolar, higher multipolar, all that depends on these properties of the sources. So I hope it is clear why it is quadrupolar. Now the next one. Will time also undergo stretching and compression, just like space points in gravitational field? Yes, it does. Now, why are we not seeing it? Why are we using mirrors and masses in the interferometer instead of two clocks separated by 4 kilometers? Look at their relative time. We could, but you see, when I showed the metric, you notice that the space is multiplied by 1, whereas time, dt square, was multiplied by a c square. This will appear again when you talk about the effects on clocks and distances. So the time will stretch and compress, but with a 1 by c square factor. Okay, so it is the stretching of time and the compression of time that is smaller by a factor c square, the square of the velocity of light, compared to the movement of two masses in space. Now, square of the velocity of light is a very, very large number, 10 to the 17 meter square plus second square. So meter per second square. So therefore, the effects on clocks will be 10 to the 17 times smaller. The tidal field is Gm by r cube. So now, for a tidal field to be very, very large, the object has to be very close by. Therefore, you know that both sun and moon generates tides on Earth. But the moon tide is more effective than the sun. The moon is much smaller than the sun. Both are effective, but moon is being much smaller. You would have normally expected its effect should be smaller, but it's much closer. Therefore, the r cube term becomes comparable or larger than when you consider between the Earth and the sun. So therefore, moon is very significant for the Earth's tides. So similarly, the answer to your question is already there in the peculiarities of the tides on Earth. Moon has a weak gravitational field compared to sun, but its tides are very, very large. On the other hand, if you look at a black hole, there's a relation between its mass and radius, and you can calculate what the tidal field compared to potential is. For every black hole, the gravitational potential has to become of order 1 near the horizon compared to the constant called c square. So gravitational potential divided by c square is of the order of 1 unity for every black hole. But the tidal field can be very large or small depending on the size of the black hole. For a small black hole, the tidal fields are very, very large. That's why in popular literature on black holes, people say if you go near a black hole, you will get stretched out due to tides. But if you go near a supermassive black hole, 10 to the 8 solar masses and so on, which are plenty in the universe, the tidal field there is even smaller than the tidal field due to Earth. You can go there very near without having any tidal distortion of your body. Gravitational wave also bends in a gravitational field like an optical field, like an electromagnetic wave. So when you, even when it passes Earth, it converges a little bit because of the Earth's gravity. near a black hole, it will converge even more. So gravitational wave gets distorted when it passes through any object. It focuses and so on. Bends, focuses, anything which can happen to a wave because of a interaction. Now the last question here. Why do gravitational waves diminish as 1 by r? As opposed to electromagnetic waves. It is not true that electromagnetic waves diminish as 1 by r square. They also diminish as 1 by r. All transverse waves, all radiation diminish as 1 by r and not as 1 by r square. It should be clearly understood. It's very important. That's why we are able to see gravitational waves from very, very far away. The gravitational field, just like the electric field, diminishes as 1 by r square. But the gravitational radiation, the wave, or the electromagnetic radiation, is the transverse part of this field. Because a charge or a mass has accelerated, there is a transverse part, perpendicular, or along the direction of the motion, which is perpendicular to the radial field, radial 1 by r square field. And that reduces only as 1 by r. And I try to motivate this by pointing out the Gauss picture, in which the radial field diminishes as 1 by r square because the surface area increases as r square. Therefore, the flux density reduces as 1 by r square. Now, radiation being a transverse field, it is like the circumference of a sphere. The circumference is just a circle, the size of which increases only as circumference increases only as r. Therefore, the intensity of the wave reduces only as 1 by r. Okay, that's the answer. So that's the end of questions here. So I seem to have finished the questions in the list.